In this section, we'll focus on discrete probability distribution. The objective of a probability distribution is to list out all the possible outcomes and their associated probabilities. For discrete probabilities, it can come in the form of a table where the outcomes are listed as discrete numbers and not intervals. It can also come in the form of a bar chart that has gaps in between values on the x-axis. Some characteristics of discrete probability distribution that we should be mindful about are that all the probabilities captured should be between 0 and 1, and the sum of all the probabilities involved should add up to 1. The values of x must be exhaustive, which means that every observation can be accounted for under one of the x's. Lastly, the values of x must be mutually exclusive, which means that each outcome can only fall into one category and not overlapping between two categories. In this example, we are told that a salesman sold between 0 to 5 phones a day, and some past info are given. If x is the number of phones sold in each day, then translating into a frequency distribution table, we get the number of days that 0 phones were sold is 5. The number of days that 1 phone was sold is 15, and so on and so forth. The total number of days should add up to 100. To construct the probability distribution, we need an extra new column for the probability. The number of days that 0 phones were sold is 5 out of a total of 100. So the probability is 5 over 100. The number of days that 1 phone was sold is 15 out of a total of 100 days. So the probability is 15 over 100. Do the same for the rest. Check that all the probabilities for this column add up to 1. To get the graph for the probability distribution, plot the number of phones sold each day on the x-axis and the probability as the y-axis. Now when x is equal to 0, probability is 0.05. When x is equal to 1, probability is 0.15. Now when x equals to 2, probability is equal to 0.3. When x is equal to 3, probability is 0.25. When x equals to 4, probability is 0.2. When x is equal to 5, probability is 0.05. And we have got ourselves the probability distribution. We know that a random variable can take on different values, each with an associated probability. So with so many different values, what do we expect the random variable x to turn out to be in the long run after conducting many experiments? The expected value will tend towards the mean of the discrete random variable, which is the weighted average of the values of all the possible outcomes. What is it weighted against? Well, it is weighted against its chance of occurring. Hence, to get the expected value of x, or E of x, or mu, we take each x sub I and multiply by its probability P of x sub I, then sum them all up. In this example on phone sales, we are to compute the expected value, which means we can use this formula. First, let's create another column for x sub I times P of x sub I. To get that, we take the x sub I in column 1 and multiply with P of x sub I in column 3. When x sub I is equal to 0, we take the 0 and multiply it with the 0.05 to get 0.00. When x sub I is equal to 1, we take the 1 and multiply it with the 0.15 to get 0.15. Do the same for the rest. Then sum up this whole column and you should get the expected value of x as 2.55. The way the expected value should be interpreted is that in the long run, the salesman can expect to sell an average of 2.55 phones per day. The keyword here is in the long run. Variance and standard deviation are measures of the dispersion of the discrete random variable x. How far is it from the mean? How wide is the spread? To find out, we define variance as the squared difference between the random variable and the mean. So in the long run, what do you expect the spread to be like? Well, the variance sigma squared is expected to tend towards the weighted value of x minus mu, whole thing squared, weighted against the probability. When expanded out, this first formula shows the summation of the squared difference between each x sub I and mu, weighted against each probability p of x sub I. The second formula provides an alternative to make computation easier, which we'll employ most of the time. Finally, to get the standard deviation sigma, we take the square root of the variance sigma squared. In this example on phone sales, we are to compute the variance and the standard deviation. To get the variance, we use this formula, bearing in mind that we found mu to be 2.55 earlier. First, let's create another column for x sub I squared times p of x sub I. To get that, we take column 1, multiply by itself, then multiply by column 3. When x sub I is equal to 0, we take 0, multiply by itself, and then multiply by 0.05 to get 0.00. When x sub I is equal to 1, we take 1, multiply by itself, and then multiply by 0.15 to get 0.15. Do the same for the rest. Then sum up this whole column to get 8.05. To get the variance, we take summation of x sub I squared times p of x sub I, which is 8.05, minus mu squared, which is 2.55 squared. That should bring us to the answer of 1.5475. To get the standard deviation, take the square root of the variance to get 1.24 phones per day. This can be interpreted as, in the long run, the number of phones sold can deviate by 1.24 or slightly more than one phone away from the mean.